So the first step is to create an initial design space of our model. Initial design space should include the biggest possible uh, available volume. Now, while creating this model, as you can see, the part should fit the assembly, and some areas around the bolting areas and ring here should be kept untouched by the algorithms. So in order to prepare model for CogniCAD, we need to create an assembly of design space and so-called the non-design features that should be laying inside the design space, as you can see here. So please note that the non-design features should be laying inside the design space. They should overlay. This is very important. Now, also make sure that all the bodies are solid and enclosed volumes, solid and watertight. So this model can be exported as step file and imported further into CogniCAD. Let's log in the CogniCAD. Once you log in the CogniCAD, each user can see its own projects and models. So let's create a new design and import the step file which we created in step. Once we imported our model in CogniCAD, we can see our model in GUI. On the left hand side we can see a tree, right, the design domain, the non-design features. We can hide and hide each object in the assembly. Now we follow the right hand side 6-step panel in order to set up a problem, which is very easy and intuitive. So let's just follow the guidelines of the right hand side panel. So the first step is to define material properties. We can select any material properties from the library. If some material doesn't exist in our library, user can always go and edit material properties like density, Young-Poisson ratio, Young modulus, yield stress, and so on. So let's select aluminum as material. Next step is to select our design space. Let's select the non-design features. We have to specify which parts in the assembly are non-design, which should be untouched and preserved. So apparently I would like to select all bolt bearing areas and the ring. So the next step is to define loading conditions. So for users which are less experienced in finite element setup, are like industrial designers or entry level of CAD users, they can use the CogniCAD engine, AI engine. So in cases where loading conditions are not known, user can click this button, click next. We have to select our application field, either automotive, aerospace, medical, or industrial design. Let's say this part is for industrial design. We click next. User have to specify the boundary conditions. Basically, the boundary conditions, these are the areas which should be preserved, should be restrained against movement. So user can always, assuming that our part is fixed in bolt bearing areas, we fix this and by clicking next, we have to specify what is the fraction of material we would like to use in order to reduce weight. So let's say if we want just to use 10% of all this volume to specify our material. Now we have to define our load cases, and so we have two options: to ask AI engine to define loads for us, or we'll define them manually. Defining load cases manually gives us much more freedom and flexibility. So first we select either we handle static or vibration loading cases. Assuming we have static load cases here, we have to define our boundary conditions. Boundary conditions means how much our model is restrained against movement. So assuming these bolt bearing areas are fixed against movement in XYZ direction, we select all these objects. If for some reason one of parts, for example, can move in Y and X and can be only fixed against Z, this is Z, this is a way of modeling it. Next is to define loads on parts. So by clicking on the part, we can immediately see that we have a vector of force. We can go and edit. And CogniCAD support forces moments. We can also define pressure on faces and then specify magnitude of the pressure in megapascal. We can define acceleration load cases, meaning we have g-forces. A user can specify the weight, non-structural mass weight of the part which is handled here, and additionally we can specify the g-force in terms of acceleration and in terms of g, and also specify the vector of application of the acceleration. And additionally, user can specify the thermal loading condition. Thermal means how much change in temperature we have on the given part, and we have to specify, of course, the coefficient of thermal expansion. So now let's specify the loads apply on the ring area here. So as we mentioned, we can edit the force component. Let's say we have 1000 Newton in direction X and Y, and we have a rotation moment of 100,000 Newton millimeter, and we can see exactly how it's applied. Now, in many cases in sophisticated modeling, we can have remote point, and loads can be applied via remote points. So the way we model it, we can specify here the point, and user is able just to edit, to move this point anywhere we want. We can specify the exact coordinate and to specify where this remote point is located. By putting it back to center, we are able to have it as well. So let's say we have this first load case, we click save, save. The second load case, if we have the same boundary conditions, user is asked to copy boundary conditions. And we can specify again the force component, maybe the same force, but rotation moment in the different direction. Now it's minus 100,000 and minus 100,000. And we can click save. Now every time user can see the load cases in left panel, we can always see it in order to check that the direction is right. And let's say the third load case will be a little bit different. We will fix it here. And we would like maybe to apply rotation moment on the group of objects. So the way we model it, we can select 2 or 3 or 4, as many objects as we want, and immediately we will have here button called group edit. We can click on it, and we have a remote point connected with objects. So if we will apply force or moment, it will be applied simultaneously on all parts here as well. And of course, this remote point can be moved everywhere, and the coordinate can be specified here. So assuming we would like to apply rotation moment on all 8 objects, we can select here group edit, and the coordinate of remote point will be automatically located in the center of mass of all objects, and we can specify 250,000 Newton millimeter rotation moment. Once we click apply, we can see the equivalent loads applied on 4 parts. Clicking save, so we specify 3 load cases. First load case when these fixed in moment and force. Now we have also the other load case when we fix here, and we have rotation moment on bearing bolt areas. Next. So once loading conditions are defined, we have to specify what are our design goals, what we would like to achieve. So there are two options here. The first is classical compliance problem, where user have to specify the amount of material it would like to use, and the algorithms, the CogniCAD algorithms, will maximize the part stiffness. So by selecting the first option, we have, for one load case, it will be just minimum compliance. Compliance meaning stiffness. If we minimize compliance, in physical terms, it means we're maximizing stiffness. So we can specify here the weighting factor for each load case. In terms, some load cases are more important than the other ones. We can put more weight on given loading conditions. And once we selected this option, we can go and select what is the fraction of material user would like to use in order to maximize the stiffness. The second option is that when we want to directly, without guessing, what is the volume fraction, we would like just to minimize mass and under specifying stress and stiffness constraints. So by selecting this option, the objective function, our goal, is to minimize mass. Once we click constraints, we can specify various stress constraints per each load case. So by default, stress constraints are 70% of the yield of the material, but of course, user, based on loading criteria like SN curves, maybe fatigue, user can go and specify stress limit, which will be lower per each load case. These can be different loading condition per each load case. Additionally, user can specify the compliance constraints, stiffness constraints. So stiffness constraints are specified in terms of Newton. It's basically force multiplied by deformation, Newton by millimeter. So if you know what's the load on given part, and you want to limit the deformation, we can specify this term here. So stiffness cannot be zero. Zero means no deformation at all. It's very rigid. And very soon we will also add deformation and vibration constraints. So for this simple example, let's specify minimum compliance problem, and let's use only 10% of material volume fraction and run the optimization problem. And the final step is to select the design setup and manufacturing method, resolution, and optimization speed. So we offer two manufacturing methods. The first is additive manufacturing, when user can specify the overhang angle and investment casting constraints. So let's select here additive manufacturing with typical overhang angle of 45 degrees. We select next step the resolution, low, medium, high. Resolution means the finite element discretization. We always suggest to users in the first step to run a minimum compliance problem and also to run a low volume fraction in order to see that design setup is correct, because low resolution runs faster and design can be achieved much quicker and in lower cost. So running low resolution and seeing what the stress levels, final design will suggest to user to run medium or high resolution and with stress constraints. So user can always change the speed of calculations if we want to run it quicker or slower. As speed increases, of course, the cost of the design increases as well. So we can see here that low resolution and slow speed cost 3.9 tokens. If we increase the speed, of course, computational resources that we spend are higher. That's why the amount of tokens are higher here as well. And if we increase resolution and speed, number of tokens increases accordingly. As resolution getting higher, design quality improves usually. So having set this problem with low resolution, slow, maybe let's run it fast to have design quicker. We click design, and our problem will start running. While optimization is running, we can see the progress here in our design cabinet. You can see how model is evolving, how many percent of optimization has been completed. User, if for some reason user thinks that design is not going in the right direction, you can always stop the model, edit, and rerun again. Here we can see that after 50%, our structure getting more and more shape. It's evolving more and more. Again, if for some reason user thinks that is not going in the right direction, you can always stop and rerun the problem again. So we can see here that the first model which we ran already 84% and almost done. It's getting very nice organic shape as a preview. At the same time, I'm running the same design case where loads are not manually specified. We use AI engine to specify loading condition for us, and we see also the second problem is started running. The beauty of cloud platform that we can run as many design cases as we want. It's so once design is generated, we can see that design is done in 32 minutes, optimized. We can click on the preview and the design is organic and nice shape is can be observed. We can go and click view in order to see it in more details. So here we go. We can see the design. The bounding box can be hidden, unhidden here. We can see very nice blend between the sharp non-design edges and the shape. The model is smooth and watertight. STL can be downloaded and printed directly and also available as a step file. So here we can see for deformations in direction X, Y, Z, total deformation. We can click simulate in order to see exactly how part deforms. On the left hand side we can highlight the loading condition and we can see exactly we have force and we have rotation moment. Let's see exactly how it behaves. And second load case, it's the opposite direction. It's exactly, we can see it like this. And the third load case, we can see that this is our situation. We can also see the von Mises stresses for each load case. We see that here about 78 megapascal von Mises stress, 120 megapascal, and so on. So additionally, if model is very complex, we have clipping capabilities here, which you can clip through and observe model from inside if needed. So as a preparation for additive manufacturing, we can also see here the button for additive manufacturing. The CogniCAD suggests also on the optimal build orientation. So if this was going to be the build plate, the minimization of unsupported areas is this. All unsupported areas are highlighted in red color, and we can see where support structures should be located. The next version of CogniCAD will also generate the support structures, so model can be downloaded including support structures. So if model is in our satisfactory, we can go and download the model. We can also see that model is converged. We see the total volume of optimized part. We can see the weight of the optimized part, the compliance, basically the stiffness for each loading conditions. And we have here two buttons, download STL and download step. We can go down ahead, download both files, and we can go to manufacturing or bring our step file back into assembly. So the optimal model as a step file I imported back into our assembly. Again, our design bounding box, and we can see exactly how it perfectly fit our assembly. So we closed the loop. We started with CAD. we have our final optimal design automatically generated as CAD file in the assembly.